Okay, this is Unit 3, Day 4b. So this is, when we're done with this, we're going to have a quiz, or well, I guess we'll have a SWIC tomorrow and then a quiz. But this is kind of wrapping up, reviewing what we did yesterday and then taking it a little bit further. So my learning targets, I can use the properties of logarithms to expand and condense logarithmic expressions. That was yesterday's. And then I can use the change of base to describe the transformations of logarithmic graphs. If I can talk right. So that's a little bit new. So refresh yourself on these. So we got the product rule and the quotient rule and the power rule from yesterday. I want you to take a moment, try these out here. I want you to, sorry, I paused it and tried to clear my throat, and here it is, it's still here. So pause the video and try these four. Okay, I want you to try those four out. Expand, condense, expand. Express in terms of natural log of 2 and natural log of 5. And then expand it. So go ahead and pause the video and try those out. And then here are the answers. So there's your warm-up. Double check them. Again, pause the video again, double check. See if all that makes sense. Try to think of anything in there that would really throw you off, but I tried to show my work on a lot of that. So yeah, so try that out. And like I said, this one I expressed it as, I took 200, I broke it into 2s and 5s, so 2 to the third, 5 to the second, and then expanded it to get this, okay? Now, I want you to go on down, try A, B, C, D, E, and F, and this is strictly asking, is it true or false? So this is a true or false statement. I want you to try those out too. So again, this is some review. So pause the video, do A through F. Then actually pause the video and try it. No, really, you should pause the video now and try it. Okay, and here are the answers. Hopefully that made you laugh a little bit. But identify as true or false. So this one here, this one is false because it would be true if you were just dividing m by n. If it was 1 log base a of m over n, this would be true, but this is false. This guy over here, in fact, this would be change of base. You could say log base n of m. Also, this would equal that, so that would also be true, but the way it's written is false. Over here, again, that's false, not the property. This one is true because it's a power property. If you think of this divided by c as the same thing as 1 over c times that, now that is part of being multiplied, so it can be an exponent of m, so that does make it true. This guy is false. You can't just, it's not like a distributive property, you factor a 2 out. That's not the case. Logarithms are not like binomials. E, that's just the definition of the product rule, so that's true. And then this guy here is not true. If they were being multiplied together, that'd be true. But since they're being added, there's nothing you can do, so that is not true either. Okay, so at the bottom now, again, this is kind of review too, so this guy here, says, given that log base b of 2 equals a and log base b of 5 equals b, what would be log base b of 10? So if they're both log base b's, I could rewrite this as log base b of 2 times 5, which would be the same thing as log base b of 2 plus log base b of 5, which would just be a plus b. A plus b from up here, a plus b. Here, 50. Well, how could I get 50 using 2s and 5s? Well, it'll be log base b of 2 times 5 squared, log base b of 2 plus 2 log base b of 5, because the 2 would come out front, and then this would be a plus 2 times b, so a plus 2b. This one here, log base b of, and I'll just, I could say 4 is the same thing as 2 squared, so put 2 out front, minus log base b of 5, so this would be 2 times a minus b. So 2 times a minus b. We can use the properties of logarithms to write an expression using only common logs, and this is just a change of base. the change of base here. So this one here, if I did common log, so this would be log r divided by log 2. And I can't simplify that because log 2 is not a nice neat whole number. I don't know what the exponent is for 10. That gives me 2, so I'm done with that. This guy here, common log of x plus y over the common log of 2. And then this guy over here, this will be the common log of x plus y over the common log of 1/3. Now with this guy here, I could separate this even more. Like keep going, because 1 divided by 3, I can actually split that. So this would be common log of 1 minus the common log of 3 on bottom. And now 10 to what power equals 1? So it'd be 0. So this is actually a 0 here. So this would equal a negative log 3 with a log x plus y on top. So anytime you have a fraction in the argument like that, split it with subtraction. You can actually simplify it a little bit further. So again, this is actually 0. 0 minus log 3 would be negative log 3. Okay, on the back side now, this is actually something you'll probably you'll use some when you get to calculus. This whole idea of rewriting it, factoring something out, factoring constants out. It will make things easier when you get to calculus. But use the change of base formula. So using the change of base formula, we can say that log base b of x is the same thing as, and I'm going to use natural logs. Okay, and I'm going to use natural log. So natural log of x over the natural log of b. Now remember, b is a constant, x is a variable. So this would be the same thing. Instead of having natural log of x divided by natural log of b, I could say this is 1 over natural log of b times the natural log of x. Okay, which means you're basically just taking the natural log of x times a constant. Because if b is a constant, take the natural log of that, you get another constant, and then 1 divided by that is another constant. So you get a constant times the natural log. And anytime you multiply the function, the whole function by a number, it's a vertical stretch or a shrink by the factor of 1 over natural log of b. Okay, so you're just you're changing it vertically. You're stretching it or shrinking it. So if this number is, when you divide it, you get a number larger than 1, it's a stretch. If it's less than 1, then it's a shrink. Okay, so what we could do is, if I give you the log base with any base of x, you could use the graph of the natural log of x or the graph of the common log of x, and that's what we'll do here, and just transfer it a little bit or stretch it, shrink it, whatever the case may be. So on this one, if I want to graph log base 5 of x, I want to do it, how would I transform natural log of x to get that? Okay, to get this. So what is it? What kind of a vertical stretch or shrink is it on this to get that? Because they have the exact same special point. They both go through 1, 0. How much of a stretch or a shrink is it? So I'm going to rewrite this. So g of x as the natural log of x over the natural log of 5. That's change of base formula. That's the same thing as 1 over natural log of 5 times the natural log of x, which means I'm just taking the natural log of x and I'm doing some sort of vertical stretch or shrink on it of this. I need to figure out what it is. Is 1 over natural log of 5 larger than 1 or less than 1? And if you put in the calculator, it's 0.62. Because it's less than 1, that's a shrink. So this is a vertical shrink of a factor of 0.62 on the natural log of x. So if you know the graph of natural log of x, take all the points and you're going to shrink them by a factor of 0.62. Whatever the y value is, multiplied by 0.62, and that's their new value. This guy here, so h of x equals, I want to write this as the natural log of x over the natural log of 1/4. Be the same thing as 1 over natural log of 1/4 times the natural log of x. So this is my vertical shrink or stretch, we're not sure yet. Now if I put that into the calculator, I get negative 0.72 natural log x. Okay, now this 0.72 means shrink. What does that negative mean? That negative means reflect. So So this is going to be a reflect, not reflex, reflect about the x-axis. So I'm going to reflect about the x-axis and then vertically shrink. I'll just write out reflect about x, then vertically shrink by 0.72. So if you had the graph of the natural log of x, do this stuff to it, and that's what the log base 1/4 of x graph would look like. This one here, I'm going to use a common log instead. So same thing, same function, just do a common log instead. Now it's going to be a slightly different one because I'm going to be doing a vertical shrink or a stretch on a different function. I'm going to do it on the common log versus the natural log. So if I do this, so h of x would be the same thing as the common log of x over the common log of 1/4, which is 1 over log 1/4 times log x. So I'm taking the graph of log x and I'm multiplying by this. This is my vertical stretch or shrink. Well, this I put in the calculator. It's actually it's a 1.66 log x. Okay. Sorry, negative. I thought that sound looked weird. So it's a negative, so that means reflect about x-axis and then vertically the stretch or a shrink. Well, this would be a 1.6, so it's going to be a stretch by 1.66. So both of them require reflecting about the x-axis, and that kind of makes sense because a natural log and a log are both going to be going up and to the right. This one's going to be going down and to the right, I guess down to the right a little bit like that. But this one, shrink it by 0.72, but that one, stretch it by 1.66. You'll end up in the same spot. They'll both have the exact same graph when you do it. Okay, so last guy down here. Okay, now this one here, we're going to do what's called re-expressing the data. So sometimes it's helpful to transform data by adding a function to one or both of the variables. In this case, we're going to actually do both of these. So we want to re-express the data in table 3.2 in terms of their common logs. So let me show you how to do it. So first off, put these in your calculator and list 1, list 2, just normal. Okay, so put them in like normal. If you need time to pause it and put that in, but put those in just like that. Okay, and let's just real quick look at this. Let's see what this plot looks like. And it sure, whoops, get that out of there. Delete this. Okay, so it definitely looks logarithmic, but it just kind of makes an L shape too. I mean, I'm not really sure. It could be like the reciprocal function too, for all we really see here. So what we're going to do is, sometimes if you re-express all the data, like take the log of everything, if it is logarithmic, when you take the log of both sides, it'll actually become a straight line. And it's a lot easier to see, is a straight line straight versus is a curved line the right kind of curve that we're looking for. So what we're going to do, we're going to go back to that data, and I want to take the log of everything in here. Okay, so it's probably let's do it this way. I'll just do it. We don't have to replace it. I'm going to put all of L1, I'm going to put that data in L3, but I'm going to see the log of it. And kind of the fast way of doing that, make sure your cursor is in L3, and I'm going to push log, and then I want to do the log of the whole first, so I'm going to do second L1. What this is going to do is every spot, it's going to take the log of whatever is in L1 and put the answer here. So think of it as an Excel document. So it's like recalling back to this, and it's going to do an operation on that. So it did the log of 0.2 and got negative 0.699, took the log of 2 and got 0.301, and so on. I'm going to go over here, make sure you're in the top column, and do log. And I want to do of L2. So second L2. And it's going to take, so the log of 420 is 2.623, and so on. Okay. And now let's look at what that data does. Okay, so I'm going to go turn this plot on, and I'm going to let x list and y list be at L3 and L4. So I want to do a scatter plot of those logarithm data. I didn't really show much. Let's go back and turn this off. and that looks a lot straighter. So this is all of that previous data, but I took the logarithm of everything. And if it's pretty straight, then that's pretty good. So now they want me to do the regression for this. So I'm going to go stat, and again, I'm doing a linear regression because it looks pretty linear now. Whoops, go back to 4. So linear regression, again, I want to use L3 and L4 because that's the re-expressed values. I don't want to do it for these because it's not linear at all. This data is not. That's L1 and L2. So store Y1. Then let's graph that guy. And that looks pretty good. Okay. So this is compute a linear regression for this. Oh, I should have left it on the screen there. Superimpose the graph. So this is step C right here. But going back to B, let's see. Do that again. So it looks like, what do you say, the expected pulse rate equals A, whoops, which is, I'm off the screen. So we got log of the expected pulse rate equals, let's see, A, which is going to be negative 0.297 log of the weight, W, plus, and then B would be 2.364. And then, so now use the regression equation to predict the pulse rate for a 450 kilogram horse is a result close to the 38 beats per minute reported by A.J. Clark. So I'm going to type this in and see if I get about 38. Okay, so let's see, I'm going to plug in. I'm going to use my calculator, I think, on this one. So here's my line out. I'm just going to trace this guy because I want to plug in 450, but I'm plugging 450 in for W. So I'm going to plug in the log of 450 into this, and what comes out should be my answer. So make sure you're on the blue line. I want to type in, and this might actually be off the graph, so it may tell me there's something wrong with this. Yeah, so I need to go to my window, make my X max maybe a little bit more. Let's go to 10. And then let's see, so trace, again, make sure on the blue line, and then log 450, because I'm plugging in 450, but that's one of these real values. I want it to be the log of that. And it looks like my Y value is going to be 1.576. So that 1.576, that's going to equal the log of PR, our predicted, or my pulse rate predicted. And log is 10, so if I took 10 to the 1.576, that actually equals my predicted pulse rate. Okay, you can put that in your calculator. You get 37.67. And that's awfully close to the 38 that A.J. Clark came up with. Okay, so re-expressing data, right now that looked really difficult, and you think, why? How did that help anything at all? Well, the re-expressing part helped us see that it really is logarithmic, because when I took the logarithm of both the variables, it made a straight line, and a pretty good R value and a pretty good R squared, and so I could work with that.